We're in section 4.5 on page 5 of our part 2, chapter 4 notes. 4.5 is summary of curve sketching. This section discusses sketching a comprehensive graph given any function f of x that includes extrema, monotonic intervals, inflection points, and concavity. Steps for graphing a function f of x. First, find the domain in any asymptotes that we have. We should also add in here to find any intercepts. X and y intercepts. Step 2 says find the derivative and critical values, which are found by taking the derivative and setting them equal to 0, and also where the derivative is undefined. And then step 3 says to find all possible inflection points from the second derivative, which you would set equal to 0 or figure out where the second derivative is undefined. The next thing that we're going to do is create one number line to summarize steps 1, 2, and 3. We're going to go ahead and break apart our domain into intervals by those possible inflection points and those critical values. And then on an xy plane, we're going to plot extreme values, inflection points, asymptotes, and intercepts, and sketch with detail each portion of the graph between extrema, inflection points, and asymptotes. So on to page 6. There's an example at the top of the page that says sketch the graph of f of x. And we have a polynomial as our function. So the domain of our function is going to be all real numbers. So domain is all real numbers. And also we have no asymptotes. So we have no asymptotes. It's a polynomial. There's no horizontal asymptotes, no vertical asymptotes, and no slant asymptotes. So the next thing that we have is we're going to find our x and y intercepts. So our y-intercept is found by setting x equal to 0. So we have y equals 3 times 0 to the 4th minus x, 8 times 0 to the 3rd plus 6 times 0 squared plus 1, which works out to be just 1. So we have an ordered pair, which is 0, 1. I'm going to underline that so I don't lose it. Next thing to find is the x-intercepts, which are found by setting your function equal to 0 and solving this. So when you set this equal to 0, this does not factor nicely. And we had tools that we learned in pre-cal called the rational zero test, and we could use that. However, it's very time consuming, so we're going to just leave it like this. We can't factor it. So right now I don't know if we have x-intercepts. We might. They might be something that's a decimal or a fraction, something that's difficult to find, or maybe we don't have any at all. So we'll leave that. The next thing that we need to do is find our critical values, which would be by finding the first derivative, which is going to be 12x to the 3rd minus 24x squared plus 12x. Setting this equal to 0, we can factor out a 12x, left over with x squared minus 2x plus 1, which factors to x minus 1 squared. And setting each of these factors to 0, you get x is equal to 0 and x is equal to 1. And these two values that we have here, these are your critical values. So next we need to figure out our possible inflection points. So in order to find your possible inflection points, we need to find a second derivative. So finding our second derivative, this is going to equal 36 x to the 2nd minus 48 x plus 12. And again, we're going to set this equal to 0. You can factor out a 12. We're left over with 3x squared minus 4x plus 1. And continuing to factor this, we have 3x minus 1 and x minus 1. And solving each of these using that zero product property, we have x is 1/3 and x is 1. these two values are your possible inflection points. And again, to determine if they're actually inflection points, you would have to see if the concavity is changing at those values. So from here, I'm going to make a single number line, and I'm going to break that single number line up based upon those critical values and those possible inflection points. My number line is all real numbers because that is the domain of this function that we have. And on the side over here, I'm going to go ahead and put my first derivative and my second derivative. And the values that we have for critical values and possible inflection points are 0 and 1 and 1/3 and 1. So there's 3 different numbers that we have. So 0, we have 1/3, and we have 1. So I'm going to kind of break this up. I'll use a different color into these intervals that we have. And we're going to look at the function and see if it's increasing, decreasing, and look at the concavity also. So let's start with the first derivative. The first derivative tells us if it is increasing and decreasing within each of these intervals. And so anything less than 0, we need to test into our first derivative. So if you substitute something less than 0 into your first derivative, which is up here, you will have 12 times, let's say, just -1, so -12. And then the next thing is -1 minus 1 squared would be positive, so this would be a decreasing. Again, we discussed if you guys feel better, you can actually substitute in something and say, like, what is f of -1, f prime of -1? So from here, from 0 to 1, if you were to substitute something in those intervals, up above, and if you do 0.2, you can do anything you want, but you'll end up with a positive value for both of these. So this is increase and increase. And then anything larger than 1 is going to be 12 times, let's say, 2, and that's positive. And then x minus 1 squared is always positive, so this would also be increasing. So our function changes from decreasing to increasing at 0. Now we're going to look at our second derivative. And our second derivative, we need to substitute in a value that's less than 1/3. So if you were to substitute in a value less than 1/3, you would have, and we'll just do 0, you have 12 times -1 times -1, which would be positive. So that would be concave up, and concave up for that. And the reason why both of those are is because it doesn't change at 0. The concavity doesn't change at 0. That's not a possible inflection point. It only changes at 1/3. So the next interval from 1/3 to 1, you'd have to select something in between 1/3 and 1, say 2/3. And if you were to do that, you would have 12, and then 3 times 2/3. The 3's would cancel. You have 2 minus 1, which is positive. And then 2/3 minus 1, which is negative. So that would be positive times the negative is negative, so that would be concave down. And then the last interval is from 1 to infinity. Selecting something larger than 1, you should get that that's going to be a positive value, and that would be concave up. Again, if it helps for you guys to actually work it out, then work it out with a number to see. So we have different intervals and different things that are going on, and we're going to now break it apart and look at each of these intervals separately. So the first one is it is concave up and decreasing. And back in section 4.3 we had a graph, 4 different pictures that showed what those all look like. So it's a decreasing function, but it's concave up. So it's going to look something like this. And then concave up and increasing is going to look something like this. And then concave down and increasing. And then concave up and increasing. So the next thing to do is we need to go ahead and try to graph our function and on our coordinate plane down here. And instead of counting by ones, I'm going to count by 1/3. Just makes it a little bit easier to graph. So actually this would be a 1 here. This would be -1. This would be 2 and -2. You can graph it any way that you want. It just makes it a little bit cleaner, a little larger to see. So we're counting by 1/3. And likewise, I'll do it with the vertical distance also. So we'll count by -1 here. This would be 1, and so on. And then 2, we'll put those in, and -2. First thing that we have, so we're going to look at everything, is I'm going to put in I have a y-intercept at 0, 1. So x is 0 and y is 1. And that's the only ordered pair that we know for sure as of right now. The next thing before we start graphing the rest of it is let's find, it does say on your steps to find your extreme values and your inflection points. So let's first talk about your extreme values. Do we have it goes from decreasing to increasing. So we have a local min at 0, f of 0. And so we need to figure out what f of 0 is. If you plug 0 in, we get 0, 1. So the point that we have on there, which is our y-intercept, is also the local minimum. So we would have no x-intercepts. Inflection points. So it changes from concave up to concave down at 1/3. And at 1, it changes from concave down to concave up. So we have 2 inflection points. We have one at 1/3, f of 1/3. And the other one is at 1, f of 1. So we have 1/3, and when you substitute that in, I get about 1.4. And when you substitute in 1 into your function, you get 1, 2. So I'm going to go ahead and put those two values on. So 1, 0, 1, our local min we already have on, our inflection points, 1, 2. And then our other values at 1/3, 1.4. So do the best you can with graphing that. Okay, so now from here, we have to graph each of these intervals that we have. So the first one that we have is from -infinity until 0. And I am looking over here. So from -infinity to 0, it is concave up and decreasing. So something along those lines. And again, we can't determine it exactly. So everyone's graph is going to have the same points and the same curvatures, but not exactly the same. The next interval from 0 to 1/3 is concave up and increasing. So concave up and increasing. And then it switches at 1/3 from 1/3 to 1. It's concave down and increasing. So concave down and increasing. And then our last interval here from 1 to infinity is going to be concave up and increasing. Again, it's kind of choppy. I would always kind of clean it up a little bit, make it look a little bit better. So concave up and then concave down.